right, today we're going to be talking about the 100 prisoner problems, which I will relabel as the 100 hungry student problem. Mildly more of a tongue twister, but also less scary, as we will see right now. So, what is the problem? Well, okay, my version 100 students will get $10,000 each if they win some game the teacher's going to give them. Yes, the original version is about prisoners on death row. So you have 100 prisoners instead of 100 students. And if they win, they don't, they get released instead of killed. That's got various moral implications involved with it that I don't really want to get into. So we're going with the students because it's way more happy. I hope no one's going to do something terrible with $10,000. I could be wrong. Yep. So here's the game. Classroom with 100 boxes with student numbers on the inside of them. So I have that up here, if you can see, boxes 1, 2, 3, and 4, and so on, up through 100. And inside each one of them is a student ID number. So the 100 students have all been given a number 1 through 100. And this is student number 26, as you can see, is the paper inside box 1, student 93 in box 2, 12 in box 3, and so forth. All right, what do they got to do? Well, the students come into the room one by one, and they get to open up to half the boxes. If they find their student ID, yay, they win. And if all of the students find their number, the whole student group wins. Everyone gets the $10,000. If any student fails, if even one fails, everyone loses. No one gets any money. Sadness overwhelms, right? So, some ground rules. It's okay to discuss their strategy before they start the game, but as soon as the first student walks to the door to enter the room, there is absolutely zero communication allowed for the rest of the game. And this includes sneaky communication, like, cell phones, laser pointers, moving things around in the room or leaving little marks on something, waiting a certain number of seconds to exit the room, depending on what you find. All this stuff is off limits. They cannot in any way pass any information to each other once the game begins. So that's the deal. They get to open half the boxes, each one, hope they find their number, and if they do, they're good, and if everyone does, they win. So the question becomes, what should the students do to have the best chance of winning? They want $10,000. They want to stop eating ramen and not get scurvy, right? Okay, so what do? So anytime we're faced with a problem, let's try to make it as small and simple as possible and start adding complexity as we go to get to the real problem. So what if we did allow them to communicate? One rule they're not allowed to do. What if we just let them do that? What's going to happen? And what if there weren't 100 students? What if there's just 4? Let's see what happens. So, yep, the first student has a 50% chance to find their number. They're allowed to open half the boxes. So, in a 4-student game, each student is allowed to try 2 boxes. Great. So let's say student 1 decides, you know what would be a great idea? I'm just going to go in there and open some random boxes and see what happens. They happen to open boxes 3 and 4. And they find their number. Yay, they're happy, right? But not only did they find their number, they saw both the numbers 1 and 4. Their number as well as student 4's number in box 3. So they leave the room and they blab to everybody, right? Tell everything. You know what? I opened boxes 3 and 4, and I saw the numbers 1 and 4. So, students 2 and 3 do the exact opposite of what I just did. Open boxes 1 and 2, basically. And student 4, make sure you open box 3. So basically, all of the other students can find their number immediately if we allow communication, right? Like, they opened half the boxes. Everyone else gets to open the other half of the boxes if the first student didn't see their number. So this works for 100 students too. You can imagine them going in and opening 50 boxes. I hope they have a really good memory, but let's assume they do for the moment, like, photographic memory, whatever. They basically just say, okay, I saw the following 50 numbers, including my own, if they succeeded. And let's say to make it easy, they just opened boxes, 1 through 50. So like they just open the first 50 boxes. They see their number and they see 49 other numbers that they list off by their crazy memory. And then any student who hears the number called just goes in and opens boxes 1 through 50. And then any student who didn't hear their number called just goes in and opens boxes 51 through 100. Simple as that. With communication, the students can actually win 50% of the time. That's the best they can do, right? Without actually cheating and going into the room and like sneaking in and finding out where your number was to begin with. The best the students can do is 50% because the first student goes in there and can only open half the boxes. They don't know where their number is, and therefore they have a 50% shot of finding their number. But after that, everyone gets their number. Okay, not too bad, right? Well, okay, let's put the no communication part back in. And let's say they don't really have any plan. They're just going to kind of YOLO this and everyone's going to open a random 50 boxes and hope for the best. What do we expect to happen in this case? Well, every student has a 50-50 chance, a 1/2 chance of finding their number when they go in. So with a 4-student game, what this means is the chance of them all succeeding is actually 1/2 times 1/2 times 1/2 times 1/2, 4 times. This is something from statistics. When you have independent events, which means they don't influence each other, they would influence each other. For instance, the student, upon finding their box, just removes their box from the room. Then that messes with the odds a little bit. But since the room is the same every time and they open a random 50 boxes out of the 100, every student actually has a 1/2 chance of this working. And the chance of all 4 of them working then at the same time is just multiplying those 1/2s together. So that's the MN rule if you care about it from probability. But nonetheless, this means that 4-student game, 1/2 times 1/2 times 1/2 times 1/2 is 1/16 of the time the students are going to win. All of them together, I mean. So that's a 6.25% chance of winning the game. The 4 students get $10,000. That's not great, right? Like that's most of the time they're going to lose this. So it gets much worse though when you have 100 students. That's 1/2 times 1/2 times 1/2, 100 times. And there's the incredibly ridiculous number of zeros in front of some, small percentage, whatever. I don't even want to think about that number of zeros. So to put that in perspective, you're actually more likely to win a major lottery twice in a row than for the students, 100 students, to win this game one time if they played every day for 100 billion years. That's right. On one side, you have the students playing every day for 100 billion years. You personally are still more likely to go and play the lottery twice in a row right now and win than those 100 students would ever win that game once. That is terrible, terrible, beyond my comprehension, terrible odds. So, can they do better? So what if they had a basic plan? So what is this basic plan? They still aren't allowed to communicate, but the 4 students basically get together beforehand, and rather than just staring dumbly at each other and then starting the game, say, you know what? What if the first half of the students 1 and 2, just pick the same half of boxes, and the other 2, you pick the other half. So what might this look like? Well, let's say the first half of the students 1 and 2, decide, you know what? We're going to pick the even boxes. Students 3 and 4, you pick the odd boxes. All right. That's a plan before they even go into the game. And then they just do it. Like they never communicate anything once they start the game. Students 1 and 2 go in and pick boxes 2 and 4. Students 3 and 4 go in and pick boxes 1 and 3. As you notice, they're going to win, right? That's how I've got the boxes lined up here. 2 and 4. The even boxes have students 1 and 2 in them. The odd boxes 1 and 3 have 3 and 4 in them. But here's the key piece to notice. Notice if the first half of the students succeed, they will always all succeed. Why? Well, if the first 2 students go in and they pick their even numbered boxes and they happen to be right, students 1 and 2 happen to be in those 2 boxes in some combination, either 1, 2 or 2, 1. there's only two other boxes the other numbers could be in, right? Because they're not just randomly going in and picking 50 boxes anymore, or sorry, two boxes in this case, but half the boxes in general. But they've decided the first half picked this set of boxes and the other half picked the other set of boxes. So if the first half are right about their first set of boxes, there's nowhere else for the other student numbers to be than the other half of the boxes. Okay, what does this do for us? Well, in the 4-student game, they all succeed if the first two students succeed. So 1/2 times 1/2 is 25% of the time. That's a decent bit better for winning $10,000 than 6.25%. I'd much rather have a 1 in 4 chance of winning $10,000 than 1 in 16. Like 1 in 4 seems like I might be able to press that luck. Maybe. Probably still going to lose, but whatever. The 100-student game also does go quite a bit better, but still horribly bad, as we'll see in a moment here. Remember, we have 1/2 times 1/2 times 1/2 now times 50. If the first 50 students succeed, there is no other possibility but that the other 50 students will now succeed choosing the other 50 boxes. So this is only 1/2 times itself 50 times. That's a slightly less scary percentage, but that's still a mind-numbing number of zeros. And this actually increases our chance to, you know what, if we played every day for 100 billion years, the chances of the students winning $10,000 will happen about 3.2% of the time. Yes, that's right. Even playing once a day for 100 billion years, they still only have a 3.2% chance of winning, but way better than like double lottery in a row kind of odds. So wow, things got better, and wow, they're still really, really terrible. But at least there's only 2 reallys in there rather than like 20 or something. So fine. You're like, well, this isn't looking too hopeful for these poor 100 students. They're going to be eating ramen a lot still, apparently. But there is a surprising fact to this game, which is why we want to look at this one. It turns out that we know the first student can't do better than 50%, even with communication, right? That part wasn't too surprising. That is the top we could ever expect them to do without communication. If even with communication, they can only get 50%. The surprising piece of information is that there is a strategy that is actually rather simple that allows them to win just over 30% of the time. So we actually don't get that far off that 50%. Even more surprising is this 30% is true even if you have way more than 100 students. Notice with the other 2 strategies, if we had 4 students, they had actually a decent chance of winning, like relatively speaking, compared to the 100 students, right? The 100 students were astronomical odds, quite literally, I think, because, universe is not 100 billion years old. So how on earth could we have millions of students and still have a strategy that wins just over 30% of the time? That's what we're going to program today, is that all the different strategies. This is going to be very similar to what we did in the last lesson. If you remember right, we did our analysis tab of the Monte Hall problem, and we used separately the Monte Carlo method, which just says, just have the computer try the game a bunch of times and then report how many times you actually won versus lost. So we're going to do that again. We're not going to do the tabs. We're not going to do the actual play the game ourselves part of this. We're going to keep things simpler. So we're just doing the analysis tab. We're just going to have it run through this game tens of thousands or more of times and just have it report probabilities. We're going to run into some different things than we ran into the first time, and we're going to learn some new tricks about how to go after them. But the idea is, and I'm not revealing the strategy yet, but we're going to get there. We're going to try these main strategies out and see how they perform.